What are photonic qubits in quantum computing? Have you ever wondered how light can be used to perform complex calculations? Let's talk about photonic qubits and their role in quantum computing. Photonic qubits are a special type of quantum bit that utilize photons, which are particles of light, to carry quantum information. Unlike classical bits that can only be in one of two states, 0 or 1, qubits can exist in multiple states at once, thanks to a property called superposition. Photonic qubits encode these quantum states in various characteristics of photons. This can include polarization, which refers to the orientation of the light wave. It can also involve the path the photon takes, the time it arrives, or even its frequency, which is related to the color of the light. Each of these properties can representing the qubit states of 0 and 1. One of the great advantages of using photons is that they interact very weakly with their surroundings. This means photonic qubits can maintain their quantum coherence for longer periods, making them less vulnerable to noise and disturbances. This quality is essential for reliable quantum computation and communication. Additionally, since photons travel at the speed of light, they can be transmitted over long distances through optical fibers. This makes photonic qubits particularly well-suited for quantum communication networks. There are several common methods for encoding photonic qubits. For instance, polarization encoding uses horizontal and vertical polarization states to representing the qubit states of 0 and 1. Path encoding involves two different optical paths, where the presence of a photon in one path corresponds to 0 and in the other to 1. Time-bin encoding uses the timing of the photon's arrival to convey information, while frequency encoding employs different frequencies to representing qubit states. Another interesting aspect of photonic quantum computing is that it typically operates at room temperature. This is in contrast to many other types of qubits that requiring extreme cooling to function properly. Photons can be manipulated using optical components like beam splitters, phase shifters, and waveguides, which are integrated into photonic circuits. However, there is a challenge with photonic qubits. Photons do not naturally interact with each other. This makes it difficult to create two-qubit gates, which are essential for universal quantum computation. To address this, researchers use techniques like measurement-induced nonlinearity, which involves additional photons and detectors to create effective interactions and entanglement between photonic qubits. In the realm of photonic quantum computing, there are two main approaches: discrete variable and continuous variable methods. Discrete variable photonic quantum computing uses distinct photon states, such as polarization, to representing qubits. Continuous variable methods, on the other hand, encode information in continuous properties of the electromagnetic field, like amplitude and phase. Some researchers are even looking into hybrid approaches that combine both methods to improve performance and scalability. Photonic qubits play a vital role in quantum communication technologies, including quantum key distribution, which allows for secure communication. They also show promise for scalable quantum processors that can be integrated on photonic chips. This integration can take advantage of existing fiber optic infrastructure and established photonic technologies. Overall, photonic qubits are a key element in the evolving field of quantum computing hardware, especially for applications that requiring long-distance quantum information transfer and operation at room temperature.